Thank you for the introduction, and thank you for inviting me to give a talk at the Winter School. I appreciate the opportunity. Yeah, so today I'm going to talk about joint work with Tobias Dyckerhoff and Jan Kile-Kili. And I think I looked a bit at the list of participants, and I think probably the majority of the people here have already heard a version of this talk before. At this time, I tried to make it quite different. So hopefully there is some new things for those who have heard this talk before. What I want to do is to try to convince you that the partially Rao-Fukaya categories of symmetric products of marked disks, once one looks at them all together, are a really fascinating object. And what I will try to do is to explain some of the relationships between the various these various partially Rao-Fukaya categories and how do they relate to some interesting constructions in homological algebra. Okay, so let us start. So as some kind of maybe as a gimmick, here is Pascal's triangle. So one way to maybe explain at the end some of the symmetries present among these categories will be by relating them to Pascal's triangle, to a certain categorification of Pascal's triangle. Now, I want to start with some kind of point of view that I learned from a paper by Dyckerhoff and Kapranov called Triangulated Surfaces in Triangulated Categories. But I think the idea, at least some part of it, goes all the way back to Kontsevich. So I want to tell you first about what are exact n+2 angles in an A-infinity category. And I don't think Kontsevich used this. I mean, I don't know, but I don't think he used this terminology. But what he did is he introduced a certain A-infinity category, which is defined in terms of a cyclic quiver with n+2 vertices. This is a graded quiver where all the arrows with label x have degree 0, and all the arrows with label, well, the unique arrow with label y has degree m. So m is a fixed integer greater than or equal to -1. And then what one does is one takes the path category of this graded quiver. So this is a graded category, a graded K category. And there is a distinguished multiplication of arity n+2, which corresponds to composing. So at every vertex, you can compose all the arrows going around the cycle. And the point is that this operation should return the identity at that vertex. And then so this is up to cyclic permutation. So this should be true at every vertex in this quiver. And all other A-infinity operations vanish except the ones required by unitality. So why are these A-infinity categories interesting? Well, A-infinity functors out of these A-infinity categories classify interesting diagrams in a fixed A-infinity category A. So let's say A is an A-infinity category. So let's start by the first case. So what's C-1? So C-1 has only one vertex and one arrow from that vertex to itself, so a loop of degree -1, such that μ1, which is the differential of y, which is now the unique arrow, is the identity of that object. In other words, an A-infinity functor out of C-1 to A is nothing but an object equipped with a null homotopy of its identity map. But that's just a zero object in the A-infinity category A. Z0 now consists of two objects connected by arrows x and y, both of degree 0 in this case, such that μ2, which is the composition operation of x and y in either direction, returns the identity of the corresponding objects. Now, an A-infinity functor from Z0 to A will be then an isomorphism in the category A, in the A-infinity category A. Now, maybe just also remark that this category is defined somehow strictly. So I define it in such a way that, for example, for Z0, we have something like a freestanding strict isomorphism. But the fact that I'm using A-infinity functors means that I'm actually required to specify certain homotopies exhibiting these maps as inverse of each other up to homotopy. So I go one step more to C1, now have three vertices, 0, 1, and 2, with arrows x of degree 0 and one arrow y of degree 1. And again, now the triple composite of these arrows will be the identity at every object. And in particular, so all other operations will vanish. In particular, the composition operation of any two consecutive arrows will be 0. And this is, by definition, an exact triangle in the sense of A infinity categories. And continuing like that, just by analogy, I may call an A infinity functor out of M into A an exact M+2 angle. So in other words, the A infinity category of functors from Cm to A is just A infinity category exact M+2 angles. Okay. Now, so it turns out that there is a very nice and simple symplectic interpretation of exact M+2 angles, or in other words, of how can one understand this A infinity algebra or A infinity category C that I described in the previous slide. So as Sibylle explained last Friday, I think last Friday, there is such a thing called the partially wrapped Fukaya category, in this case of a surface, in this case the disk, with, in this case, M+1 mark points on its boundary. So the construction is due to Aru, who modified a construction of Abu Said and Seidel, who had constructed the wrapped Fukaya category of a surface with boundary, or, well, yeah, maybe, yeah, I'm not sure exactly in which generality they construct the wrapped Fukaya category, actually. But nonetheless, Aru introduced this modification, which now takes into account the existence of stops. Maybe for Louisville domains or something like this. I'm actually not quite sure. And in any case, so I can take, so in this case of the surface, of a surface, Lagrangians are simply arcs. And what I have done here is I have selected 6 arcs in this Fukaya category. Now I fix n equals to 5, arranged in this way. Now, it turns out that after choosing certain grading structures on these arcs, so yeah, something I think maybe I don't know if this was explained on Friday, but one important point in this case is that the datum of an object of this partially wrapped Fukaya category is not just a Lagrangian, but a Lagrangian equipped what is called a grading structure. So I'm not going to explain what grading structures are. I'm just going to claim that there is a choice of grading structures. Oh, sorry, a choice of grading structures such that the derived endomorphism algebra of the direct sum of these objects in this partially wrapped Fukaya category is quasi-isomorphic to this A infinity algebra Cn-1 that I described in the previous slide. So now, roughly, why is this the case? So here are some rules of how one computes in this category. So among arcs of this kind, one can compute the morphisms between them by sliding the endpoints along the boundary component following the orientation of the boundary, which is determined by the orientation of the disk. So in this case, for example, there is a map from L01 to L05 obtained by sliding this endpoint of L01 until it collides with this endpoint of L05. Similarly, there is a map here by sliding this endpoint to this endpoint, a map here, a map here, a map here, and a map here. So this gives us the cyclic quiver I described in the previous section. Now there is a further rule which says that I cannot compose maps that are obtained by sliding endpoints at different boundary components of the surface minus the mark points. So, or I mean, I can compose them, but the composition returns 0. So this explains why the pairwise composite of all these arrows is 0. And as James explained in his lecture series, the existence of this polygon here in the middle is what it's taking into account for the existence of this Higher multiplication mu m+2 that I had explained in the previous slide. Okay, now it turns out that this is a redundant generator of the partially wrapped Fukaya category. In other words, I can throw this blue arc away and just keep these arcs marked in orange, and that is a generator of the Fukaya category in the sense of triangulated category. So that means that the smallest triangulated subcategory of this partially wrapped Fukaya category, which contains these objects and is closed under direct summands, is the ambient category itself. Okay, so in particular, this arc is in the thick closure of this orange arc, so I can completely ignore it. And it turns out, more or less as I explained, that the derived endomorphism algebra of these Lagrangians marked in orange is now isomorphic to the path algebra of the linearly oriented quiver with n vertices modulo the square of the ideal generated by the arrows. So here I'm working, if you want to blur a field, but all these calculations work also over an arbitrary commutative ring K. And now it's a theorem that perhaps belongs to the folklore of Fukaya categories, that this algebra is derived equivalent to the partially wrapped Fukaya category of the disk with n+1 mark points on its boundary. So I'm not so sure to whom one should attribute this result, but one maybe should mention the names of Ahu, Kontsevich, Seidel, and perhaps many other mathematicians who have observed this equivalence in various different guises. So now, okay, so this was to say, how could one somehow obtain this A-infinity algebra in a symplectic way? So here's another class of diagrams which are also interesting, which are called, well, I don't know if there is a name for them, but I call them Higher octahedra in A-infinity categories. And I think the calculation of this specific A-infinity category, which is a full subcategory of the derived category of the A-n quiver, is due to Hermes in 2014. Maybe there is an earlier calculation, but I am not aware of it. So I don't know, there are many representation theorists in the audience. Those people will all recognize this as the Auslander-Ritten quiver of the module category of the path algebra of the A-n quiver with linear orientation. So how is this A-infinity category defined? Well, it's just the path category of this graded quiver where all arrows have degree 0 except the arrows labeled tau, which have degree 1, which are labeled tau because they correspond to the so-called Auslander-Ritten translation in this derived category of the A-n quiver. And there is an additional data in this A-infinity category, which are several ternary composition operations, which express the fact that every time I look at such square, which are the squares that give the so-called Auslander-Ritten triangles in the derived category, and I form the following complex in the perfect derived category of this category, I denoted Mn. So this is supposed to stand for modules for the A-n quiver. This is now an exact triangle in the sense explained before. And again, A-infinity functors out of this A-infinity category mu Mn to A classify n octahedra in a fixed A-infinity category A. Okay. So what's the symplectic interpretation of this higher octahedra? So again, I look at the same partial wrapped Fukaya category of the disk, n+1 mark points on its boundary.
Gustavo?
Oh, yes?
It seems that there is a problem and the pages of the presentation are not updating.
The pages of the presentation are not updating. So let's see if we can.
And then now the screen sharing, I think.
Yeah, I tried to start it and stop it again.
Thanks a lot.
Okay. Sorry. So you stayed here, right? Or what was the last part you saw? Did you see this at all?
No.
Oh, okay. Okay, so now you will recognize the Auslander-Ritten quiver of the module category of the path algebra of the linearly oriented A-n quiver. So here is the Auslander-Ritten quiver. Now I take the A-infinity category defined as the path algebra of this graded quiver, where the arrows corresponding as their translation have degree 1, and such that some natural diagrams I can form in the perfect derived category of mu n are exact triangles. So this mu3 is part of the data of this A-infinity category. And this classify n octahedra. Okay, so that was the point. And this in the calculation of this A-infinity algebra is the one that I think is due to Hermes, as far as I know. Okay. Now, what's the symplectic interpretation of this higher octahedra? So just go back to the same partially wrapped Fukaya category, disk n+1 mark points on its boundary. And now I throw in all the arcs, which represents the isomorphism class of objects in this Fukaya category up to shift. It just looks like this. Again, there exists a choice of grading structures such that the derived endomorphism algebra of the direct sum of all those objects in this Fukaya category gives me this A-infinity category mu n. Again, I can choose, this is a highly redundant generator. I can take, for example, all arcs that start on a fixed boundary component of the disk minus the mark points. In this case, I chose the component I labeled with 0. And it turns out that the derived endomorphism algebra of this direct sum of arcs I labeled with in orange is now just the path algebra of the linearly oriented AN quiver with no relation. So this comes again from the fact that I can slide these endpoints so that they collide one to one another. Again, it's essentially the same theorem, because of course these two algebras, the path algebra of the linearly oriented AN quiver and the same algebra but modulo the square of the ideal generated by the arrows, are derived equivalent. Okay, so can you still see the screen? Yes, it seems so. I think I can check this on. I think I can check this on my screen as well. Okay, so yes, so one way to understand what happened here between these two different equivalences with these two different algebras is through Koszul duality. So here I have two collections of generators, one labeled with a V, which are in my mind dual generators, and these other ones would have no V. These are the usual generators of that will give me the path algebra of the AN quiver. So it turns out that this endomorphism algebra is a Koszul A-infinity algebra, so it's formal, and its Koszul dual is also formal. So I denote them, this algebra and its dual by Koszul dual by. So this turns out to be the Koszul dual of this algebra. This is AN check. And with respect to some different choice of grading structures as before on the Lagrangians labeled with a B, so that the morphisms between them have now degree 1, because the Koszul dual of the path algebra of the AN quiver is now generated in cohomological degree 1, corresponding to the degree of the extensions between the simple AN modules. Then is now a special case of a general result of Bernard-Keller on Koszul duality for augmented DGAs, that there is an equivalence given by Koszul duality between these two categories, which makes this diagram commute. Okay. So, any questions so far? Should the slide have changed? Yes. Okay. Sorry. Okay. So, yeah. So it seems there are no questions. So I'll just continue. So these are all, in some sense, rather simple observations, but there is something quite interesting, which is that the various derived categories of AN quivers, or in other words, the various partially wrapped Fukaya categories of the disk with different numbers of mark points on its boundary, have a very, how to say, very structured relationship between them, which is what I will try to explain now. So I want to explain a type of functor that relates these partial wrapped Fukaya categories, which are called stop removal functors. These are due to Roux in the case of symmetric products of surfaces, and to Sylvan more generally. So what's the starting point? So take the disk with n+1 mark points in its boundary, and identify lambda n with lambda n minus 1. So this is the collection of mark points minus, let's say, the last mark point. So it turns out that there exists a functor which will be a Verdier localization, which is called stop removal functor, which relates the disk with n+2 mark points on its boundary to the one with n+1 mark points on its boundary. So what's the idea? Well, the idea is basically you should look at arcs on the disk simply. If you have a configuration of arcs on the disk with all mark points, you can look at it again without one of the mark points. So for example, let's look at this one. So I have 3 arcs which form a triangle. So this triangle here actually encodes a triangle in the Fukaya category. So this I have indicated here. Now this Lagrangian, which is close to the last stop, in this Fukaya category is non-zero, because this stop prevents it from being contracted to the boundary. But once I map it to the Fukaya category of the disk without that stop is not there, so this actually will become a zero object of that Fukaya category. In other words, these two arcs will become isomorphic, which makes sense because now these arcs are homotopic to each other. And in fact, so this is called stop removal functor. In fact, the stop removal functor has both adjoints, left and right adjoint, and its kernel is generated by this, by a choice of an arc covering the last stop, just as I have indicated here with L5 check. So in particular, this forms what's called a recoulement. So if you don't know what's a recoulement, it means that there is this sequence of a fully faithful functor I and another functor S, such that I is the kernel of S, and such that, well, what is written here, so that iota has both adjoints and S has both adjoints. So this will imply, in particular, this category here is the Verdier quotient of this, the one in the middle, by the essential image of the one on the left. So that's already nice. But of course, one observes that this choice of mark point was arbitrary. I could have chosen any other of these mark points and performed the same operation. So in other words, I have at least, what is it, n plus 2, is it n plus 2? 0? Yes, I guess the way I wrote it here, n plus 2 stop removal functors going down one step. And I have this for all n, right? And all of them have fully faithful adjoints. So what does this mean? Well, what this means is that the stop removal functors and their adjoints give this collection of categories, which I would like to identify not with the perfect derived category of the A-n quiver, but of this other A-infinity algebra mu-n. This form now what is called the simplicial triangulated A-infinity category. So the relations that are satisfied by the stop removal functors and their adjoints they're called simplicial relations. And this actually is a simplicial triangulated category in let me just say in a coherent sense. So by a disequivalence, one can establish the coherence of the simplicial relations combinatorially. And then there is another approach by Tanaka by something called stacks of broken paracycles, which I actually don't know exactly what they are. But this is supposed to give an approach to establishing the coherence of the simplicial relations using only symplectic geometry. So here, the way one can obtain this simplicial structure is by having this specific, is essentially a combinatorial model of this category where this simplicial structure becomes immediately apparent. And this is exactly given by these stop removal functors and their adjoints. And here's another theorem that belongs to the folklore now of something called algebraic K-theory, which is that if you take an A-infinity category, which is triangulated and idempotent complete, so it's, well, even, let's say it's of the form of perf A for some small A-infinity category A. Yeah, that's what I want to say. Yeah, triangulated and idempotent complete and small. Then there is a certain monoidal operation on such triangulated A-infinity categories. And if I take the tensor product of this partially Raphukai category with A, I obtain the category of cells of what is called the S construction of the triangulated A-infinity category A. So for n equals to 0, these both are 0. So when this is the case when this has only one mark point. And this is, so the simplicial object that I obtain in this way is called the Waldhausen S construction, which is, as I will explain in the next slide, the main ingredient in the construction of the algebraic K-theory space of a triangulated A-infinity category. And now there is an additional symmetry that is already, it's immediately apparent when I look at the disk, which is that I can rotate the disk by a factor of 2 pi over n minus 1. And rotating the disk with carryover corresponding to certain shift gives the Waldhausen S construction what is called a paracyclic structure, which I don't want to explain exactly what it is, but it means it has additional symmetry in this case. So the Waldhausen S construction is defined for something more generally called the Waldhausen categories, where this paracyclic structure may not exist. So as I mentioned, the Waldhausen S construction is used to define the algebraic K-theory space of an A-infinity category. So this is due, partly to Waldhausen and Thomason, who applied it maybe in the case of derived categories of schemes, and this is somehow similar, same construction. So if you have a triangulated A-infinity category A, the Waldhausen K-theory space of A is obtained from this Waldhausen S construction, by passing what is called, so degree-wise, one passes to what is called the underlying infinity groupoid of this triangulated infinity category, and takes its geometric realization, which will yield a CW complex. So I'm sorry, I will not explain any of this in detail, but basically the idea is that this symbol here means that there is a canonical way to construct a pointed CW complex, which the canonical mark point is given by the zero object of A. And then one takes the loop space based at 0, and that's the definition of the algebraic K-theory space of A. Now, the point of explaining this is that by the previous slide, this S construction can be described, and its implicit structure can be described in terms of partially wrapped Fukaya categories of disks. So what we see is that there is a very close relationship between the symplectic geometry of disks with mark points and the algebraic K-theory of triangulated A infinity categories, which I think is already quite interesting. Okay, so from this space, one can then define the high. So that's the main point of introducing this space. That now this is a topological space, and one can just consider its homotopy groups based at 0, and these are the algebraic K groups of A. So for example, K0 is just the ordinary Grothendieck group of A, which could have been defined by first passing to the zero cohomology category, taking the free abelian group generated by the isoclasses of objects, and modding out the relations given by exact triangles. Just to get you an idea of why this will agree, well, as I said, there is a canonical base point given by a zero object in A. Loops at 0 are identified with objects. So maybe let me go back a bit. So this comes again from this formula. So a simplicial object is basically a blueprint to build a CW complex by specifying its cells and how they are glued with each other. And the relations of how these cells should be glued are given in this case by the stop removal functors. So for S1, here we'll have delta n, so delta 1, which will be the disk with 2 mark points, which will be just the A. So this will be derived equivalent to the A1 quiver. So this is just the perfect derived category of the field. So in other words, the edges of the CW complex I will be constructing are just the objects of A. So this is where this comes from. Two simplices. Now it's easy to see from what I explained before that are given by exact triangles. So this is where one will obtain the relation that the middle term is the sum of the outer terms in the Grothendieck group. More generally, three simplices are given by octahedrons, and higher simplices by higher octahedra. Okay. Okay. Yes. So I think this is all about just the disk. So as you can see, just by looking at the disk, we already found some interesting connection to some other interesting object in mathematics, namely the algebraic K-theory of arbitrary triangulated A infinity categories. Okay, so now I want to explain what happens, or somewhat what we understand what happens once we, instead of considering simply the disks by themselves, we consider their symmetric products. Okay? So for that, I want to explain briefly what are partially wrapped Fukaya categories of Riemann surfaces with non-empty boundary. So these are due to Auroux, who introduced them in 2010 in his ICM proceedings for Hyderabad. And more recently, they had been extended to more general situations by his student Sylvan. So the input data is a Riemann surface with non-empty boundary and a finite set of mark points on its boundary. This set might be empty, in which case one will recover wrapped Fukaya categories. So then one forms what is called the symmetric product of the surface. This is nothing but the default Cartesian product of the surface with itself, modulo the natural action of the symmetric group. So the way to think about this space is just the space of unordered collections of D points on the surface counted with multiplicity so that the total multiplicity is D. So in other words, some of the coordinates of the point, some of the points might agree if some of the coordinates in this product had agreed before passing to the quotient. Oh, sorry. Now, by considering collections of points such that one of the points lies on one of the stops on the surface, one obtains also stops on the symmetric product. And then one can define this partially wrapped Fukaya category. Okay? Now, there is an improper, so yeah, one interesting thing about partially wrapped Fukaya categories is that you don't need, so thanks to the work of Auroux, you don't need to have so much intuition about how the symmetric product of a surface looks like, because you can calculate morphisms between many of the objects of this category through a very concrete combinatorial rule, which I don't have time to explain today, by only looking at arcs on the surface. Yeah. So then, just by looking at the surface and collections of arcs on it, as I will explain now, you can actually at least see some parts of this partially wrapped Fukaya category in very, very concrete terms, which is very advantageous. And why is that? Well, there is a proposition of Perutz who showed that there exists a symplectic form on this default symmetric power with the property that away from the big diagonal, so that is where any of the deep points on the surface, any two of them collide. So that means where all the deep points are distinct. Yeah, so that's the subspace of the symmetric product with all the points are distinct. Away from the big diagonal, this symplectic form constructed by Perutz agrees just with the product of the symplectic form of the surface. So what does that mean? In practical terms, it means that I have D distinct Lagrangians on the surface, so just some arcs, or maybe some closed curves, more complicated surfaces than the disk, which are pairwise non-intersecting, so that their product lies away from the big diagonal. Then I know this is a Lagrangian because now I can just restrict the form to each of the factors, and I know that each of the factors is a Lagrangian on the surface, and this will give me a Lagrangian on the symmetric product. Okay, so that means that I can consider, in other words, so that what that means is that I can consider the product of D different arcs on the surface which don't intersect as an object of this Fukaya category. Okay. And then, as I explained, then Auroux gives a very clear rule of how to compute morphisms between objects of this form, as long as these objects are arcs which are incident to the boundary. And at least in this case, there is a very clear combinatorial rule to compute. And this is in some sense enough. I mean, of course, one would like to compute always more and more and more, but Auroux also gives a rule of how to find generators of this Fukaya category, and they're all of this form. So in other words, one can always compute, in theory, an A-infinity algebra, which is derived equivalent to this partially wrapped Fukaya category in purely combinatorial terms. And in fact, maybe I should mention this, that Auroux introduced this class of partially wrapped Fukaya categories motivated by the border Hegar-Floer homology of Lipschitz-Vath and Thurston, which is a certain is a kind of intricate way to associate invariance to three manifolds with boundary. And there is a distinguished A-infinity algebra that appears there, which is called Strand's algebra. And basically, these partially wrapped Fukaya categories allows you to realize these Strand's algebras. And this Strand's algebra, these very combinatorially describes A-infinity algebra that one can eventually calculate in this way. Okay, right. Okay, so now, what I would like to do is to understand more and more about these partially wrapped Fukaya categories. And there is a very interesting proposal by Konciewicz, I think from around 2009, which is also more general, but in this specific case of partially wrapped Fukaya categories of symmetric products of surfaces, it says the following. So it says that it should be possible to describe this partially wrapped Fukaya category here as the homotopic limit of triangulated A-infinity categories of the following form. So they're going to be tensor products of partially wrapped Fukaya categories of symmetric products of disks. Now, this di is not necessarily always the same as this d, and they will have, some number of mark points. And the condition so that these categories will appear in the indexing diagram of this colimit is that the sum of the di's is d. So in other words, what you should imagine is that in some sense, every surface, if you want, has a nice cover by disks, and you want to somehow recover the partial Rab-Fukaya category of the whole surface by gluing together the partial Rab-Fukaya categories of these tiny disks that live on the surface or that cover the surface. So this is some kind of delineate type tensor product. When I write this, it just means, so these are already of the form perf. Well, I will explain this. Well, I mentioned in the previous slide that Awu explains how to get an A-infinity algebra, which is derived equivalent to this. So this is some type of delineate type tensor product. So in the case d equals to 1, there is a complete proof of this. So there's more to this proposal that I said here. So one also would like that there will be, I will explain now in an example here, there are many ways that you will get indexing diagrams for this colimit, and you would like to somehow understand also how this description as a colimit is independent from the choice of this indexing diagram in a very sort of structured way. There are many reasons why I want to do that in that way, which I don't have time to get into this. So in the case d equals 1, so that's just partial Rab-Fukaya categories of surfaces with boundary. There are different approaches. One, for example, is due to Haydn, Katsarkov, and Kontsevich, which is, they gave a complete proof of this local to global description of the partial Rab-Fukaya category, and Dikharov, Kapranov give a slightly different one, which is the one I want to explain here for motivation for what we are actually trying to do in the future. Okay, so let me try to give you an idea of how, well, both of them are quite, in some sense, in spirit, they're very similar. So what's the idea? So you start with a surface. In this case, the disk with two punctures, yes, which I see, I think of them as boundary components, and two marked points on its boundary. So what you do is you choose a ribbon graph spanning the surface. So that means that the surface deformation retracts onto the ribbon graph after I remove the macro points. So that's a ribbon graph spanning this surface. Okay, so this ribbon graph tells me how to glue together. In this case, there are going to be 4 A-infinity algebras of the form described at the very beginning of the talk. So these cyclic A-infinity algebras introduced by Kontsevich that classify exact n+2 angles. And which algebra should I put so should I glue? It will depend on the valency of this corollas here in the ribbon graph. Okay, so the way one will do this is that through the ribbon graph, one can obtain some kind of canonical representatives of some Lagrangians, if you want. In this case, I have marked them in orange like this. And as you can see, locally around each of these corollas, I have 3 Lagrangians. So in this case, the corollas have valency 3, all of them. I maybe could have chosen a different example which has corollas of different valencies. But here you can see, for example, here's a corolla of valency 3. And now there are 3 Lagrangians that form a triangle because of this big triangle here. And here I have another one, and another one, and another one. So, and of course, if you compute the endomorphism algebra, in whichever way you prefer, you will obtain something that looks like this. So let me explain these pictures. This is the derived endomorphism algebra of these Lagrangians. And notice that they are highly redundant, but it's actually convenient to draw them in this way to actually understand how they are glued to each other. So each of these triangles represent an A-infinity algebra parametrizing exact triangles. So it consists of 3 vertices, 3 arrows, so arrows between them that compose to 0, and a ternary composition such that the composite along this cycle is 1. So this is important. This is not just an ordinary algebra; it's an A-infinity algebra. And here is another copy, and here is another copy, and here's another copy. And somehow, the point is that from, in some sense, the incidence graph or the incidence category of this ribbon graph, one can obtain a certain diagram, including functors relating the perfect derived categories of these various A-infinity categories, A-infinity algebras that are associated to each of the corollas in the ribbon graph. And now the algebra that I've written here will be just the homotopy co-limit of this diagram. And I also forgot to mention here that the fact that I can go around. I mean, at least in just one direction, but I can go. Depends on the orientation I have chosen, but I can go around and around and around these boundary components. So this means that these triangles here have no relations. Okay. So then the point is that then one would like to understand very carefully how does this colimit change as I change the ribbon graph. For example, I could have collapsed this edge here, and I would like to understand, well, give me a new diagram. How are these two diagrams related, and so on and so forth. This is what is already very well understood, I would say. Okay, so before continuing, there is another reason I wanted to include this example is because here one can also visualize quite nicely the effect of these so-called stop removal functors. Because basically, what is this algebra telling me? That I have 4 exact triangles of, in this case, if you want, you can think of this. This is the category classifying 4 exact triangles in this configuration, so that their vertices agree in this way. Now, suppose that I remove these 2 stops. What's the effect of removing these 2 stops? Well, when I remove this stop, this arc becomes homotopic to the boundary. So it will become a 0 object of the Fukaya category. So in this picture, this will become a 0 object, but this was an exact triangle. So this will become an isomorphism. Similarly, when I remove this stop, this will also become a 0 object of the Fukaya category without stops. And therefore, since this is an exact triangle, this will become an isomorphism. And then what will be the result? It will be just 2 exact triangles going in opposite directions. But they will be, after I identify these 2 vertices along, and these 2 vertices along these corresponding isomorphisms, these will be just 2 triangles on the same vertices but going in the opposite direction. So this is some picture you will find on the paper I mentioned before by Tobias Dickerhoff and Mikhail Kapranov, the one called triangulated surfaces in triangulated categories. And it describes the Fukaya category of the disk with 2 punctures and no mark points, which turns out to be mirror to the coordinate cross, if I remember correctly. Okay, but you can see, so you see that, for example, by adding stops with all these redundant generators, then sometimes this simplifies by using stop removal functors, maybe simplifies the calculation of a more subtle A-infinity algebra, namely in this case the one for the same surface without stops. For example, if I wouldn't have added, so these 2 arcs, so this is maybe some things I just want to share, that so these 2 arcs are redundant because, well, there is say a morphism here, so that this arc arises as the cone of that morphism. So in some sense I could have forgotten about it, and I also could have forgotten about this arc. But if I would have done that, it would have been perhaps not immediately obvious, or it would have been, but maybe less obvious, that once I remove these stops, then the arrow here will become an isomorphism. Of course, it will come from the fact that I will be able to slide now this arc all the way here, but I don't know. I think this is a nice way to make these calculations. Anyway, okay. So let me continue. So all of this was to say that the case equals to 1 is somehow very well understood, and it's a very fruitful case in which one can really calculate many, many interesting things. And yeah, this is, as we saw in Sibylla's talk, this is the case which is closely related. This is somehow essentially equivalent to A-infinity gentle algebras or something like this, right? For example, I say infinity because, you know, maybe I have no stops, and then I have some Yeah, even with the stops, I have some A-infinity relations that I probably cannot get rid of. So I think this will be, I'm actually not sure of this, but I think this will be an A-infinity algebra, a gentle A-infinity algebra in the sense of Buckland. It should be at least. Anyway, okay, so what do we want to do? So what we want to do is we want to understand this for, well, we want to understand this in general, where we're starting by understanding how to perform this gluing description for surfaces of genus 0. Yeah? So just punctured disks. But for arbitrary powers of the, arbitrary powers. Now, why we first focus on this case? Well, there are many reasons. So first, there is a direct computation of the A-infinity algebra, or an A-infinity algebra, which is derived equivalent to the corresponding partially derived Fukaya category in this case. Yeah. So in other words, so this is due to Lekili and Polishuk, who have also computed the mirrors in that case. Yeah. So in other words, in that case, so suppose we have a candidate of how to perform the gluing, then we will obtain some A-infinity algebra. At least we have a way to check whether we get the right answer or not. Yeah. So that's the first reason. So thanks to the work of Lekili and Polishuk, we have something to compare it to. Okay. Another reason is that due to a topological obstruction, for surfaces of genus non-zero, there is no Z grading on the Floer homology complexes that one needs to consider to form these partial rough Fukaya categories. So that means that one is stuck in the world of two periodic categories. And somehow, due to the nature of the methods that we want to use, which involve stable infinity categories, which are somehow triangulated categories which are linear, not over the integers, but over the sphere spectrum, somehow this suggests that we actually should not be able to perform the construction for arbitrary surfaces without taking into account the two periodicity of the shift functor, which is now kind of a further source of complexity. And in addition, it's much harder to describe the precise indexing diagrams that one is to use to take the colimit and glue these categories described here. So we have somehow a pretty good candidate for this. So this is actually, in my opinion, quite difficult. So we have a candidate for this, but this somehow, still not quite there yet, but it's getting really close. So this is our work in progress. But from this proposal, what we see is that the first thing we should really understand is what are these partially rough Fukaya categories of disks with mark points, symmetric products of disks with mark points. So this is the main result of a preprint we uploaded in 2019, which reads as follows. So I'll try to explain this a bit carefully. So take the disk with n+1 mark points on its boundary. So here I fixed the n+ first roots of unity, but this doesn't really, the precise position of the points doesn't really matter. So it turns out that there are the following, so this actually combines several results. So there are the following equivalences of triangulated A-infinity categories. Also note here the convention that n is bigger than or equal to d, bigger than or equal to 1. So if d is bigger than n, then everything here is 0. So that's why this is like this. Okay, so let's start here. So this is the partial rough Fukaya category of the default symmetric product of the disk with n+1 mark points. By using, so maybe let me go quickly so that you have them in mind. There's maybe one advantage of this thing. Yes, here I have two collections of generators of this partially rough Fukaya category. The ones that start, so all the arcs that start at the boundary component labeled 0. Yeah, so these are all this. And the duals. The ones marked with a V. So using results of Auroux, one can check, well, no. The results of Auroux imply that separately, each of these collections of generators yield generators of the Fukaya category of the symmetric product. And so in other words, we already know that they will generate this Fukaya category. And we also know how we should calculate their A-infinity algebra of endomorphisms. So this is what we did. for the arcs that start on the boundary component 0, one obtains a rather big differential graded algebra, but turns out that it has its cohomology concentrated in degree 0, which is not obvious. And if you compute its so it's quasi-isomorphic to its cohomology. So in particular, this derived category, this Fukaya category is derived equivalent to the derived category of an ordinary algebra. And what we found out is that this algebra here turns out to be what is called the d-dimensional Auslander algebra of type A n minus d plus 1 introduced by Iyama in a completely different context, which is called higher dimensional Auslander writing theory, which is also a very beautiful topic in representation theory, but unfortunately I have no time to explain what that is and how can one visualize the higher Auslander writing theory of this algebra. Maybe I'll explain a little bit implicitly in this Fukaya category, how can one see this higher dimensional AR theory inside here. Okay, so that's the first result. Now, the second result, which is obtained by taking the dual generators. Well, first one observes, that's not so difficult, that the dual generators are still Kosul dual. So there is a Kosul duality equivalence obtained by general results of Keller again that makes this diagram commute. And now it turns out, so one knows this algebra is Kosul, so its Kosul dual will also be formal. And up to shift, so this is now what comes here, up to shift is a different higher Auslander algebra, now is of dimension n minus d. So if I apply this theorem, now by substituting d by n minus d, I get this triangle here. So this is the same theorem, but for different values of d, so d and n minus d. And as I explained, by shifting the degrees, the gradings on the generators, we can make all the maps between the generators have degree 0 and obtain a different higher Auslander algebra. And I also should say that a direct equivalence between these two algebras concentrated in degree 0 was obtained by Beckert as part of his PhD thesis, who used a very intricate calculus of what were called stable derivators. And this is in fact then just a special case of his calculation, which in some sense works over the sphere spectrum while we work in some sense over the integers. On the other hand, Beckert does not explain any connection with symplectic geometry as one sees here. Okay, so something which is interesting to observe here is that by going like this, we obtain an equivalence between Fukaya categories associated to symplectic manifolds of different dimensions. So this has dimension d, complex dimension d, and this one has complex dimension n minus d. So this is, well, as far as I understood from Yankee, this is kind of interesting. So there are other kind of more trivial ways to create such equivalences between Fukaya categories associated to symplectic manifolds of different dimensions, but this is somehow not so trivial in the sense that it is in some sense an instant Kosul duality. Okay? So what's good about this is that we have a very concrete algebraic model of these partially wrapped Fukaya categories, which are the ones we actually needed to understand to eventually understand Kontsevich's proposal in this more general case. And moreover, these higher Auslander algebras are actually in some sense completely combinatorial, which is also great. So I want to quickly explain the combinatorial description of this algebra. So these algebras are defined by a very subtle homological construction due to Iyama related to higher Auslander writing theory and cluster categories. And it's a very sort of, yeah, it's like kind of miraculous construction. And Iyama in the same work when he introduced these algebras had calculated a presentation of these algebras by generators and relations as the path algebra of a quiver with relations. And Opperman and Thomas then translated this into somehow different combinatorics, which are more suitable for what I want to, well, just somehow easier to explain, I think. And in general in our work, they're more it's more convenient. So this presentation is essentially due up to a shift, let's say, of indices is due to Opperman and Thomas. So how does one proceed? Well, so first some combinatorial terminology. Given two subsets of the set of numbers from 1 to n, each of which has the elements, I will write I squiggly arrow j, read I intertwines j, if the following inequalities are satisfied. So each of these subsets inherit a total order from the standard order on the numbers from 1 to n, and this is precisely the one that induces this labeling. So I1 is less or equal than j1, I2 is less than j2, and so on. So then I say I intertwines j. So as a vector space or as a K module, so it turns out this is a free K module, the algebra A and D. It's just the direct sum over all pairs of intertwining subsets I intertwines j. So this is a directed relation, which is reflexive, not symmetric, and not transitive, right? So yeah, so I don't know how that's called. So it just gives you some arrows in some sense, right? So yeah, okay, it's a directed relation or something. And this is a formal generator of this free K module of rank 1. And the product is also very easy to describe. So the product of f from I to j with f from j to k is just f from I to k if I this was supposed to be I intertwines k, of course, and 0 otherwise. And there are no Higher products. It's concentrated in degree 0, and therefore no Higher products. So for d equals to 1, it's easy to check that one recovers the path algebra of the linearly oriented A enquiver. For d equals 2, one recovers what it's called its Higher-Auslander algebra. Sorry, it's ordinary Auslander algebra of this quiver, which I've represented here just in this way, right? So this means one takes the path algebra of this quiver, all the arrows in degree 0, the composite of these maps is 0, these squares commute, and so on. Okay. So I have maybe 3 minutes left. Okay, but I'm basically done. So again, so as you can see, these algebras are completely combinatorial. And they have this somehow very regular structure. They look like, so this is basically a line, this is a triangle. The next one is going to be a tetrahedron, and then in general, they look like a simplex. So they're very, 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 very combinatorial algebras. And it turns out that, so Agu had already considered stop removal functors in this context. And it turns out that they also endow this collection of partial Raffo-Fukaya categories of symmetric products of a disk for a fixed D with a simplicial structure. So what's happening now is easier to explain how the stop removal functor will work by introducing what are called the Orlov functors. So these are certain fully faithful functors that go from a default symmetric power of the disk with n plus 1 mark points to the d plus 1 symmetric power of the disk with n plus 1 mark points. So we'll increase the dimension by 1 and the number of mark points by 1. And what one does is that let's say on some chosen generators, one just takes the product with a small arc which is close to a new stop. So let's say the last stop that will be added from here to here. Okay, so how does this look like? So let's suppose d equals 1, so that d plus 1 equals 2. So if this stop is not there, this arc is a 0 object of the Fukaya category, and these two arcs are isomorphic, but they still form a triangle, right? Because there is still this triangle here. So I have a triangle here, such as the cone of this map is 0, and this is an isomorphism. And if I just send it to this category by the Orlov functor by taking a product with this arc, well, I will get, well, the idea is that if this is going to work, I should get such exact triangle. And it turns out that one can prove that if you want, by taking another copy of this arc so that they don't intersect and form so that the product forms a Lagrangian, one can prove that the product of two, say, equal arcs or isomorphic arcs becomes 0 in the symmetric in the twofold symmetric product. So this is something one will need to prove so that this will make any sense, right? But this is due to Agu. So then, as before, we define the stop removal functor as the Verdier. Well, it turns out that one can identify the Verdier quotient of the stop this category here by the image of the Orlov functor at that stop with this partially Raffo-Fukaya category. I had sorry, it's not that one, it's that one, but with one stop less. And that's the stop removal functor. So it goes from n+1 to n. Again, it has adjoints on both sides. And we obtain the same Reculmont situation as before. And it's just same result as before. So maybe I'll just go a bit quickly because I'm out of time. There is a higher dimensional generalization of the Waldhausen S construction due to Dyckerhoff and Poguntke, and one has the same result as before by combining with some result in another work with Dyckerhoff and Walde, where we described the cells of the d-dimensional S construction of a triangulated A infinity category A in terms of Higg-Gauss-Landau algebras of type A. So again, it's the same formula as before. We can recover the S construction in terms of tensoring with a Fukaya category. It's also, this Higher S construction is also related to algebraic K-theory. So Thomas Poguntke had proven that, basically same formula that one used for constructing the algebraic K-theory space of A, but where now we take not the loop space, but the default loop space of this CW complex. This is homotopy equivalent to the algebraic K-theory space. So this exhibits. So basically, this is what's called the looping of the algebraic K-theory space of A, and exhibits it as a connective spectrum. So for those who might know about algebraic K-theory, or of triangulated infinity categories, notice that this is not the iterated S construction. The iterated S construction is multi-simplicial, and this is just a simplicial object. And the type of diagrams that one looks, they look like this. Yeah? So let me just, so sorry, I went too slow, I didn't realize. So let me just then conclude by showing you what I said at the beginning, which was how do these partially wrapped Fukaya categories, they fit in the following categorified version of Pascal's triangle. So this is the shorthand I have used here. So suppose you work over a field. So these are all so these all have Grothendieck groups which are finite, free of finite rank. The rank of the Grothendieck groups are the binomial coefficients, and the Kosul duality statement I explained then therefore recovers binomial duality. And the Recolmonts associated to the Orlov functors and the stop removal functors, which are then here, this is just the usual recursion for the binomial coefficients. So yeah, let me stop there. Sorry for going over time.